Swayam Prabha. Digital India. Educated India.
We will go very slowly. Understanding of this is extremely important because the machines that you are going to work, the CPU that you are going to handle are basically pipelined and multi-core CPUs. Okay, fine. So now let us start. So this whole set of lecture I am organized into two parts. The first part is instruction level parallelism, where we will be talking about pipelining concepts, RTL, the register transfer level, and how do you get the speed up there. We will talk about superscalar, we will talk about very large instruction word or very large integer word, VLIW concepts. We will look at basically static instruction scheduling and dynamic instruction scheduling. Then we will do some amount of astrology called branch prediction. Okay, we will do that. Then the next part 2, we will go on to the multi-core, where we will have Amdahl's law applications, symmetric multiprocessors. What is the challenge in building a multi-core? The biggest problem that we will see is something called cache coherency problem. I did mention in the third semester course what is cache coherency. Okay, remember? No? Okay, I will repeat. Then we will look at distributed memory systems, message passing systems, parallel models of computation. How do you design algorithms for parallel process? Okay, some amount of coding. So it is not enough I say this is a very big dam. No, I should tell you how to pour good water into it. So I will also teach you some amount of parallel programming. This will be an introduction to parallel programming. Okay, so you have all done some sequential programming already as a part of your DSA lab, correct? Now we will tell you how to do this parallel programming. And then there is some OpenMP and other software available in our supercluster. Okay, so these two parts we will cover very slowly, but in great depth. Okay, so when we look at performance, right, I can't get performance just of a blue. I can't say I will write an excellent compiler and that will give me the best performance. I can't say I have a best hardware that will give me the best performance, right. I can't say I have the best microarchitecture that will give me the best performance. If I need performance, all of them have to work together, right. If I need performance, here is one timing, another is power, another is area, all these things. That is what I told you, right. If I could make a machine that needs 1 kilowatt of power for execution, nobody will buy it, correct. If I make a CPU chip which needs 1 kilowatt to execute, nobody will buy it. We need to make a system that has good power dissipation, that can be put into small form factors. So power, area and performance together make something sellable today. And so if I want to make hardware, I need to make a hardware that is sellable. What is sellable there? My power, area and performance need to be there. So suddenly I can't say no performance, I have an excellent compiler, I will invest so much on compiler, I will get the performance. It is all crap, we can't do it. Okay. So performance is an joint orchestration of several components in the system which will finally give you the best results. So when I am looking at performance, I should start looking at the circuit level, which we call as the register transfer level, RTL, right. The next thing is, now we will go and see if there is performance at an instruction level. These two we already have a glimpse, right. We designed a Wallace tree multiplier, we designed a carry look ahead adder, and there we did show that between a carry ripple adder and a carry look ahead adder there is a performance difference from n to log n, but we did increase the size of these circuits. So with some compromise in the area and the power dissipation, I could get good performance even functionally, right. So we did look at the circuit level. At an instruction level, we had looked at SIMD, for example. When we looked at the MMX instructions, we did the single instruction multiple data type of instructions. We have seen some amount of parallelism there, but this is with respect to one instruction, right. Now can I make multiple instructions run in parallel? Of course, we are going to talk about that in great detail. Then once I have one processor which has some parallelism inside it, right. So let me just summarize here. I have improved my circuit to give better performance, like I have moved from a carry ripple adder to a carry lookup adder. I have moved from a sequential multiplier to a Wallace tree multiplier. Now these things are going to give me a lot of speed. On a processor which has all these features, I am bringing in things like SIMD type of instructions, etc., and there I have built parallelism. So I have parallelism at the circuit level, I have parallelism at the processor level. Now I put multiple such processors which share a memory, which is called shared memory multiprocessor, right? Then it actually becomes now a multi-core system with many CPUs and which is sharing a memory. So I brought in more parallelism there by putting more processors. Now one chip could have multiple such CPUs and one shared memory. So this is called a multi-core chip. I will put several multi-core chips together, that actually, and each will have its own memory. So that becomes a distributed memory multiprocessor, which is the next stage of parallelism. So parallelism can be at the circuit level, it can be at the instruction level, it can be at the chip level, it can be across chip levels, right. And so today when we look at some of the modern supercomputers that we see that are executing, the speed there, the performance there essentially comes because it is not that they have hundreds of CPUs, not just only because they have hundreds of CPUs. Each CPU has multiple processing units, multi-core, and each of that core has several instructions that could do a lot of concurrent activity, and those instructions are executed on units which are also highly on circuits realized using circuits that are also highly concurrent. So when I look at a system, when I am looking at performance, it is not enough just I have a supercomputer with multiple CPUs. Each CPU could have multiple cores, each core would have multiple instructions which are concurrent, and each of these instructions could be realized using hardware that is very fast, right. So we are looking at performance at all these levels. So what we have seen so far is that we have looked at RTL, circuit level, and we have also seen some instructions that can exploit hardware which can give us some amount of parallelism at the instruction level. Now we will see more about instruction level, then we will move to SMP, then to distributed memory as we proceed on this lecture. Now what is pipelining? I have done this in the class earlier, but then I will just, for the benefit of Palagat people, I will do it once more here. Pipelining is what we term as instruction level parallelism, ILP, okay. It is not integer linear programming, okay. It is instruction level parallelism. Now where is instruction level parallelism? Let us look at where do we get that instruction level parallelism. When I want to execute an instruction, I fetch the instruction and increment the PC. The next is I decode the instruction. The next is I fetch data, then I execute the instruction, then I store back the result. These are the 5 general stages in execution of an instruction. Now what will happen is, if I have 10,000 instructions to be executed and each of these unit take 1 unit of time, then to execute one instruction it will take 5 units of time. So hence to execute 10,000 instructions it will take 50,000 units of time. Now what we see is that when an instruction is fetched, these 4 units are not doing anything. When an instruction is decoded, the remaining 4 units are not doing anything. So when an instruction is in some stage I, let us say stage 1, stage 2, stage 3, stage 4, stage 5, if it is in some stage I, all the remaining stages not j not equal to I remain silent, they are not doing anything, correct. So that means in a single cycle, in one cycle the instruction finishes off all the 5 steps, in that only at any point of time only 1/5 of that hardware is working, the remaining 4/5 is sleeping, right. So can I do something about it? So there comes the notion of a pipelining. What is pipelining? You have already seen some automobile or any manufacturing sector, there is something called a pipeline. For example, if I want to make a scooter, somebody will assemble your seat and then your body, and then somebody will be fitting the tire. While they are fitting the tire for this first scooter, the second scooter body will be assembled, and when they are putting the brake for the first scooter, second scooter's tire will be there, third fellow's body will be assembled, and so on. So this is called a pipeline, right? So similarly, the same concept is seen here with pipelining. Say I1 is fetched. When I1 is decoded, I2 is fetched. When I1's data is fetched, I2 is decoded, I3 is fetched. When I1 is executed, I2's data is fetched, I3's I3 is decoded, and I4 is fetched. When I1's results completes execution and results are stored, I2 is getting executed, I3's data is being fetched, I4 is decoded, and I5 is fetched. So the first instruction completes at the end of 5th unit of time, right? But the second instruction, when it will complete? At the end of 6th unit. Third instruction at the end of 7th unit. So a 10,000th instruction will finish at the end of 10,004 units. So by doing this, by reutilizing the hardware at what we have achieved, we have got 75%, close to 75% performance improvement. What was taking something like 50,000, we have got close to 80% improvement. What was taking 50,000 units of time, currently it finishes off in 10,004 units of time. The first instruction takes 5 units of time. The reason that is called latency, pipelining latency. Please note this word. So this is called pipelining latency, latency of the pipeline. Okay. So first instruction does not come in the first unit, it is coming in the 5th unit. But the subsequent instruction comes one after another, right. So I get this 80% speed up just like this by reutilizing the hardware. Okay. But this is a very ideal case. There can be lot of scenarios where this cannot happen as nice as this. If everything could happen as nice as this, then we don't have anything to teach. But lot of problems come up when we try to do this instruction level parallelism. But so with pipelining, we get actually a speed of close to 5. But then this will not work for several reasons. The reasons are called hazards. Hazards is one that will stop the pipeline from and there are many type of hazards. One is called data hazard, another is called control hazard, another is called structure hazard. There are 3 types of hazards: data, control, and structure. This is one very important thing. So you will not have that free flow of instruction one after another. There may be reasons why I cannot proceed pumping that instruction from one stage to another, as we had seen in the previous slide. It may not be possible for I1, I2 to come in this same speed. Somewhere I have to stop them, and the reason for stopping is called hazard. The second important thing is, I did assume that every unit takes unit amount of time. Every unit here takes unit amount of time. This is not the case, especially for the execution. For example, floating point multiplication will take 10 cycles, which is very close to an adder, but floating point division will take 40 cycles. So me assuming that everything is unit cost, right, 1 unit of time, everything can be finished in 1 unit of time, is a wrong assumption. The execute for different instruction, for I1 can be a floating point multiplication, it can finish off in 10 units of time. I2 is a floating point division, which can take 40 units of time. So I assume that every fellow finishes in 1 unit of time. What is that unit? It can be different for different instructions. So what is the reason here? The performance actually comes because of some amount of inherent parallelism that is existing among the instructions, and we will try and understand what are those parallelisms. We have already seen this type of parallelism, correct? This is called SIMD. Suppose I haven't had 100 numbers and I have 4 processors. I go and say split 100. One thing is j equal to 1 to 100, do sum equal to sum plus aj, which is a very inherently sequential process. But if I have 4 processors, the best solution is split 100 numbers into 4 parts, each of 25 numbers each, allot one part to one of the processor and ask all the processor concurrently to add the parts assigned to them. So in 25 units of time I will get the answer of 25 numbers being added, and then I will have one processor which will add those 4 and gives me an answer, right. So at the first stage what we are doing is that this is called data parallelism, because the parallelism here is because I have 100 units of data. The parallelism in the example here is because I have multiple data, right. So I had 4 different sets of 25 numbers, multiple sets of data, please understand, and to each of these 4 fellows I said add those 25 numbers. I gave one single instruction, and that is why this parallelism is called single instruction multiple data parallelism, and that SIMD is possible only if I have multiple data. If I want to operate the same thing on multiple sets of data, then there is a scope for doing this single instruction multiple data concept. On the other hand, there is something called, we talked about data parallelism, there is something called functional parallelism or multiple instruction multiple data. What do you mean by this? Multiple functions to be performed on a data set or data. So my data passes through different functional units and each one of them will do something different on that data. For example, the pipeline itself, if I assume that the instructions are data and the pipeline units are processing that itself is an example of a multiple instruction multiple data. As you see, this store data is processing I1, execute instruction is processing I2, there is no connection between them. So it is a multiple instruction multiple data type of parallelism. To sum up, there are 2 types of parallelism, data parallelism and functional parallelism. We have already seen data parallelism with some amount of thing, like we saw recursive doubling, etc. SIMD we saw the MMX instruction set, etc. Now we will have a very good instruction to functional parallelism, which is multiple instruction multiple data.